This is a favorite subject of mine. I've worked for many years on water. I haven't done any work on water quality lately, but I do find it a subject of great interest because it impacts so much of what we do. And as Tara said in her introduction, water is a unique nutrient. And it's unique for the reasons in that paragraph, but it's also unique in that we can't study water like we study other nutrients. For example, if I want to determine what is the amino acid requirement of pigs, I do a titration and I can determine what is the level of lysine that maximizes performance, or the amount of lysine required per kilogram of body weight gain or protein gain or whatever. That they can be defined. I can do that with vitamins and minerals. I can't do that with water because the physiological mechanisms that drive water, homeostasis in the pig and homeostasis in the pig in terms of its fluid environment is critical, just as it is in our bodies. There's so many mechanisms that come into play that if you deprive a pig of water, even modestly, then it works to conserve water. And so it becomes very, very difficult to identify what really is the requirement. As a thumb rule, we would say that water intake, not water disappearance, but water intake will typically be about 2.5 times the intake of feed under thermal neutral environments. And it will go up somewhat in hot environments. But don't be misled, in really hot environments, we've measured water intake that barely hits 3-to-1. So water disappearance goes up much, much more than that, but the pigs, you find, are playing with the waters and they waste a lot more water in hot environments, as well as drinking somewhat more water in hot environments. But a 2.3 to 2.5 ratio of water to feed will be fairly typical in commercial practice. So I'm going to give a little bit of an introduction on water, going to talk about how do we define water quality, because that's my subject today. How do we define water quality? Then how do we treat water to improve its quality? And then finally, what does water quality do to the health and well-being and the performance of growing pigs? I do not have any data on sows, and that is one of the deficiencies in our database. There's extremely little information on water subject matter of any kind as it relates to both gestating and lactating sows. Some excellent work done by Dave Fraser and Peter Phillips in Ottawa back in the 1980s, but that's some of the most comprehensive work that we've seen. Let's think about the role of water. And this is part of what fascinates me, because we think of water, it's ubiquitous. When we want water, we go to a tap and drink it, or we go to a store and we buy it in a bottle, for the most part for reasons that I completely don't understand. And so we take for granted that water's available, and water's generally pretty good quality in terms of human consumption, and in most cases for animal consumption as well. But let's think about water in terms of its chemical characteristics, and that really helps to explain why water is so absolutely critical in the health and well-being and the performance of the pig. So first off, water is involved in thermal homeostasis, obviously critical to life in any homeotherm like the pig. And water, unique compared to many other liquids, has a very high specific heat, meaning that it can absorb more heat energy and have a very small change in temperature. If you were to expose that same amount of heat energy to other liquids like alcohols and so on, the change in temperature would be much greater. So the very fact that water has this high specific heat makes it ideally suited to contribute to thermal homeostasis in the pig. Secondly, acid-base homeostasis. Water contributes to acid-base homeostasis in many ways, but its pH, its neutral pH of 7, and indeed the fact that most water exists in that range of upper 6s to low 8s, but most of it's in the 7s, means it's very close to physiological pH for the animal. As a solvent, it also has unique characteristics because it has this dipolar character which enhances its role and its ability to dissolve various solutes in it. So it then can act as a very successful transport medium. Nutrients and chemicals, chemical energy, metabolites, waste products can all be moved through the body from the cells where the waste products are produced to the kidney, or from the stomach, intestinal tract, GI tract to the tissue in terms of nutrients, and is very effective in moving those nutrients and waste products. And it also transports chemical signals both amongst tissues, within tissues, and within cells. So this ability to carry many chemical moieties in solution gives water a great advantage in terms of its transport role in the body as well. And it also plays a significant role in many chemical reactions. So obviously oxidation, one of the products of oxidation is water. And we're going to see how significant that is in the overall water balance of the pig later. And hydrolysis, for example, hydrolysis of proteins involves water as well. So when you sit down and think about it, there's very, very little that goes on in the body of the pig that doesn't involve water, either directly or indirectly. It really is extremely important. Here's a typical water balance that we've put together for the pig. And the first thing you'll notice is that drinking water, this came as no surprise, is the largest source of water to the pig. But interestingly, about more than 10% of the water that the pig obtains in its daily balance comes from metabolism. So oxidation, as one example, contributes a significant amount of water to the pig. So for example, if you think of a camel walking in the desert, or walking, let's say, in an environment of water deprivation, the humps on the camel are not big vats of water, okay? They are humps of fat. And fat metabolism has that unique characteristic that when fat is catabolized, it produces more weight in water than existed in the original fat itself. So it's a very efficient way, I'm overstating if I say very. It's a relatively efficient way to carry water as fat. Okay? So water metabolism, metabolism contributes a significant amount of water, and of course we sometimes forget that 10 to 15% of the feed that the pig consumes is water itself because it's not perfectly dry. On the excretion side, we might be surprised that although urine is the largest source of excretion of water, it is not even 50% of the total outcome of where water ends up. So it's certainly very significant. But feces represents a significant component. Digestion a little bit. Other, we could break that down substantially, but let's just say for the most part, this is water lost through respiration. There's sweat, of course, but that wouldn't apply very much to the pig, a little bit, but not too much. But respiration represents a large vehicle for the elimination of water. And during heat stress, of course, the pig will lose vast quantities of water through thermal panting. And that's why its demands for water increase so substantially. And then, of course, water is retained in the growing pig through growth because lean tissue, at least, contains substantial quantities of water. The ratio in lean between protein and water is something like 2.5, around 2.5 to 1, something in that range. So as the pig deposits protein in its body, it also needs water to go with that. So that's kind of what a typical water balance looks like in the pig. By the way, I forgot to mention, unfortunately our second speaker has become ill and won't be here, being nicely filled in by Mike King. So I've got a little bit more time than I would have had otherwise, so feel free to ask questions during my presentation if I'm not explaining something adequately, or if you want to disagree with me. I know that rarely happens, but if somebody disagrees or has a question, Chris. When we define water quality, I have some cautions that I think are really, really important. First off is that many standards that you will read with respect to water quality, hardness, color, odor, many other constituents of water quality, definitions of water quality, address aesthetics more than they define any health-related issues. Okay? And that's not often acknowledged. Secondly, is many of the standards that have creeped into agricultural use actually are derived from human standards. And human standards, of course, number one, aesthetics is more important. That's illustrated by the huge growth in the sale of bottled water. Right? So obviously aesthetics is really important to people, and so aesthetics are built into those standards, but they might be irrelevant to the pig, and in most cases I think they are. And in other cases, we're going to be much, much more conservative in quality standards for people than we are for pigs. The best example of that is nitrates, where the nitrate standard for pigs is about 10 times higher than it is for humans. And the human standard is basically for human infants who are being fed formula and the water that might be used to reconstitute formula. And, of course, the concern is with what's colloquially called the blue baby syndrome, or the impact that nitrates can have on oxygen binding to hemoglobin. So that would be an example where the standard for humans we know is much more stringent than it is for livestock. Okay? So the fact that these standards for animals have in many respects been derived from standards for humans causes us to pause and step back and look at those standards and determine how significant they are to the pig. And as was indicated in the introduction, because there hasn't been a great deal of research on water quality in the pig, there's been a fair bit, none in sows, for example. We really don't have enough information to come up with really hard, well-defined standards of quality for certain characteristics, and I'll talk about that in my presentation. So let's talk about then defining water quality. We can define water quality in three different ways. There's physical, chemical, and microbiological. In terms of physical, the typical measures are turbidity, color, and odor. Turbidity, of course, is the opaqueness of the water, we might call it. There are different units that are used, nephelometric, Jackson, forget what the F stands for, it's in my manuscript, but they all are the same, and they all are defined as the equivalent, one of those turbidity units is the equivalent of 1 milligram per liter of silicon dioxide. Okay. Turbidity, to me, I don't really think is something we need to worry about for the pig, but it's what makes up that turbidity that would worry me. And so I'd want to go further if there was a turbidity issue. Color is self-evident, and odor as well. And I'll talk a little bit later on about odor issues. One of the key ones, for example, can be from odor bacteria. And iron bacteria that grow in the well or in the source of water, and they create a slime, and that slime deteriorates, it rots, and creates a very foul odor that can be very difficult to get rid of. Okay, so let's going to spend a fair bit of time on chemical definitions of water quality. First off, total dissolved solids. Just as its name suggests, total dissolved solids is really just the total amount of solid material that exists in the water. It's very easily measured. You just take a sample of water, dry it off, and whatever is the residual is the dissolved solids that are in that water. So it's a very easy measurement to do. It's a very nice measurement to do if you want to just do a quick scan of water to see if you need to go any further with analysis. So, for example, if TDS is less than 1,000 parts per million or milligrams per liter, you don't really need to worry about it in terms of things that might affect the health of the pig. If the total dissolved solids is in the 1,000 to 3,000 range, you might see some transient diarrhea in pigs. If it's 3,000 to 5,000, that's an area that's very gray, and I'm going to come back and talk about that a little bit later on. And if it's over 5,000 parts per million, I'd probably be reluctant to use that as a drinking water source for my pigs. Conductivity is a way of measuring total dissolved solids indirectly. It's faster, it's simpler, it's cheaper. It's basically 2 electrodes put into the water to measure the conductivity of the water. And of course, water isn't a conductor, but the minerals within the water is. And so it's a measure of that conductivity, therefore, of the solids. And then the conductivity is multiplied by a factor that can vary from 0.55 to 0.75 to convert it to total dissolved solids. Well, that's a big range. It's not very precise, and I really don't like it. And when we request water analysis, we specifically ask that TDS be done and not conductivity, and that the TDS they're reporting is not generated through conductivity. Oftentimes, they'll just use a proxy of 0.65 to convert conductivity to TDS, but it really depends what's in that water, what that factor should be. pH is self-evident. That's the concentration of protons. As I mentioned earlier, typical water is going to be somewhere in the range of the upper 6s, possibly as high as the low 8s. Really not a problem. Sometimes we like to lower the pH of water as a way of protecting against diarrhea, particularly in young pigs, because if we can lower the pH of the gastrointestinal tract, then we can create an environment which is contrary to the growth of certain pathogens. Changing the pH of the GI tract is a lot easier said than done, however. And we've done studies with various acidifying vehicles, and thinking that the pH of the secretions in the stomach is in the range of 2 or less, and remembering that the pH scale is a log scale, so a difference of 1 pH unit is a tenfold difference. Changing the pH can be quite a challenge. But there are ways of doing it. And that's why organic acids are used, because it's really their metabolism which lowers the pH rather than just adding an acid directly. Hardness is really a measure of the divalent ions that are present in the water. They're expressed as equivalents of calcium carbonate. So calcium and magnesium are the 2 major contributors to hardness. I don't think within the range of hardness that we see in water that the pig cares about hardness. We care about hardness because it can cause problems because of the scale that's associated with it. It can cause problems in hot water heaters. It can cause problems with blockage of water delivery systems, nipple drinkers, and those kinds of things. So it's associated with delivery problems. I'm not aware of any work that really shows that it's associated with any particular health problems. I think I say it later on, but if I don't, before I forget, when we soften water through ion exchange, we merely replace calcium and magnesium with sodium. Okay, so we don't change the ion content if we use ion exchange softening. So as a consequence, then, we will end up with twice as many sodiums present in the water as we originally had calcium and magnesium, because calcium and magnesium are divalent and sodium is monovalent.
Hardness is basically how salty the water is, right?
Not really, no. Not really. It's often referred to as that. And sometimes even people will refer to hardness and total dissolved solids in the same manner, and they're not. And so thanks for asking the question, because hardness, actually, really good point. Really thanks for asking the question, because I didn't have this in my talk at all. One of the things we really need to remember when we're evaluating water quality and measuring anything in the water is that obviously water is electrically neutral, right? There is no net charge in water. So if there's sodium in water, which is a cation, there has to be an anion that goes with sodium to maintain electrical neutrality. So if we measure calcium and magnesium in the water, then that doesn't impart any saltiness, but the anions that go with calcium and magnesium can. And that's where the, quote, the saltiness could come from. So you could have calcium carbonate, and that's not going to give you any salty taste, but you could have calcium chloride, which could. That's very rare, but you could, or magnesium chloride. So good question. But yeah, we have to be careful that hardness is really just calcium and, well, any of the divalent ions, which quantitatively as calcium and magnesium, and ignores the anions that go with them. And we'll come back to the anions in a minute. In fact, maybe I'll stay with that right now just because of your question. The ions that will be present with calcium and magnesium can be carbonate, innocuous, chloride, rare. Any of the water analysis that I see, I don't know if anybody in this room has seen water analysis that are high in chloride. There's some formations that will give you high chloride, but they're relatively rare. It's much more common to see other anions. Now, if it's sulfate, then we have an issue, because if it's calcium sulfate, that's called Glauber salts, and we all know what Glauber salts will do to you. And if it's magnesium sulfate, well, that's Epsom salts, and we're even more familiar with what Epsom salts will do to us. So we need to know, if there is hardness, we need to know what the anion is that goes with it to get a proper, complete picture of the water quality. Does that answer your question?
Yep.
Okay. So then we come to sulfates, and sulfates are the real issue of drinking water quality. Iron will be a little bit of an issue, and we'll come back to that as well. But sulfates are the one that generates by far the most complaints that veterinarians would be dealing with. And so I'm going to come back to the effect of sulfate on performance later in my presentation. Iron and manganese, they're somewhat related to aesthetics, somewhat related to delivery. Iron in groundwater exists in the reduced form. When we pump water from the well and it becomes exposed to oxygen, then the reduced iron becomes oxidized iron, and everybody knows what iron oxide is, or rust, and reduced iron is soluble in water. Oxidized iron, iron oxide, is almost completely insoluble in water. And so that's why you will see, for example, red discoloration in sinks and toilets and so on. That is typically from iron. And manganese will do the same thing, except instead of giving a reddish color, it will give almost a black color, very dark brown color. And so if you see that discoloration, you know right away what you're dealing with. I'll talk a little bit later about what we can do about iron and manganese in the water. Nitrates and nitrates should be an issue of water quality and safety and health of the pig, but the research, there's only been a few trials, and the studies that have been carried out show that the pig, at least the growing pig, has an incredible tolerance for nitrates. So for example, the standard of 100 parts per million of nitrates, or 10 ppm as expressed as nitrates, there's been studies showing pigs being fed 200 parts per million nitrates with no apparent adverse effect. So the standards that we have would appear to be extremely cautious. But remember, they are higher than what is acceptable for human infants, and not to be messed around with, because for human infants it is a real problem. And back in the day, before water quality was understood, that was unfortunately a not uncommon cause of infant mortality. Sodium can be found in the water. We like to know how much sodium is in the water because of the sulfate issue, and magnesium and calcium because of the whole hardness issue. And then chloride is really important, because if I have a diarrhea problem going on in my barn, I might remove some salt from the diet in order to try to minimize diarrhea. And that's okay to do, and we've done it many, many times, but the problem is that a lot of water, which is rich in sulfates, and it also is rich in sodium, we can take sodium chloride out of the feed, and that does tend to help to reduce the diarrhea a little bit at least, but we're also taking chloride out of the feed. And a lot of waters don't have very much chloride in them. So the net result is, if we want to take out the salt, that's fine, but we got to keep in mind that we're also taking out chloride, and we might have to come back in with potassium chloride. And it still appears to be better in terms of diarrhea, but that's something because if you want to reduce diarrhea in the pig and remove the salt from the feed, and you create a primary chloride deficiency, you will have a tremendous impact on reducing diarrhea because the pig will go off feed very quickly. Chloride deficiency is a great way to stop pigs from eating feed. Okay, so do it, but be very careful. If you want to do it, the calculation is that you assume conservatively that the pig is drinking twice as much water as eating feed, so the sodium content and the chloride content in the water can be multiplied by 2 to be the equivalent of what's in the feed. Right? So you make that conversion, and that will tell you how much sodium chloride you can take out of the feed.
The other thing is if water has salty, pigs won't drink as much. They won't like it. They won't go further.
Yeah, I've got some data on that. So if you can hang on to that, okay? Because what our pigs did wasn't what I thought they were going to do. Okay? Yeah. I'm not going to talk very much about microbiologists because most of you are veterinarians. I'm not going to talk about microbiology because I don't know very much about it other than that you really want to analyze the water to make sure that pathogens are not present in the water. But there's got to be a reason to test for it. In Western Canada, where I was before I came to Iowa State, we used a lot of surface water, water collected in dugouts, snow runoff and rain runoff and so on. And of course that water source was much more susceptible to microbial contamination than groundwater was. So we paid a lot more attention, certainly on those farms that were using surface water. Okay, so let's talk about water treatment as we move along here. We can remove colloids if we want to clear up the water by using activated charcoal. It's pure aesthetics. It's pure aesthetics, so that's just a decision that you can make if you want. Certainly if you're drinking water from the same sources as the pigs are getting their water, you may want to use activated charcoal. Water softening, as I mentioned before, ion exchange is still the most common. There are new methods coming out, and there's filter methods and others that are being used, other chemical methods. But ion exchange is still the most common because it is the simplest and it's very inexpensive. But just remember, as I mentioned previously, that if you're taking out calcium and magnesium, then you are, at the same time, you are adding sodium back in. Removal of sulfates, to the best of my... Roger.
So John, is the TDS then, is that fairly neutral? Is the effect of softening the water neutral on TDS?
Actually, it should be neutral, Roger. Softening should be neutral because you're just taking out positive ions and putting positive ions back in. So there shouldn't be any effect there. Yeah. Okay. Removal of sulfates. The only way that I'm aware of that you can remove sulfates is through a process called reverse osmosis. It's the use of very, very fine filters operating under pressure, relatively expensive systems, certainly for the volumes that would be required for a hog barn, very expensive. One unit that I'm familiar with, they spent over $100,000 putting an RO unit in. That's a number of years ago, and the technology maybe have become cheaper. But I also know that in the first year, because they didn't get very good advice on the operation of the RO unit, they spent $100,000 on filters as well. So it became an extremely expensive system to operate. I've seen this in barns operate very well. Seen it in nucleus herd, genetic nucleus herds, for example, where people just don't want to take any chances. But you really have to have somebody who's an authority that understands how to manage these things and set them up. So, for example, if you've got excess iron in the water, it will just absolutely annihilate those filters. That was the problem on this other farm. And so you have to have upstream water treatment before the water ever gets to the RO unit, because otherwise the RO unit will become very ineffective very quickly. And I don't think, as you'll see later on, that under most circumstances it's really justified. Removal of iron and manganese. Filtration is the most common method. The problem that I see in barns is that the filter gets put in and forgotten about, and it does need to be maintained like any filtration system. So that's a bit of a concern. But you can put in filters that will remove iron, and they're relatively inexpensive. The other thing, as I mentioned before, iron coming from the ground will, from the ground up to the surface, converts from reduced to oxidized and is no longer soluble. You can take advantage of that. So if you put a cistern in the system between where the water is coming from and before it goes into the barn, and as long as you have about a 2-day storage in that cistern, then you can settle out significant quantities of that iron. But if you're doing that, I really advise that we should have a chlorination system upstream from that, because any cistern that basically has water sitting in it is a great place for the growth of bacteria. And so by putting in a chlorination unit, you prevent the growth of any potential pathogens in that cistern, but also chlorination accelerates the precipitation process, so that it makes it even more effective. Now this is data that goes way back into the 80s, but this was water source collected from a farm, not the best water, 1,300 ppm of sulfates, 2,400 ppm of total dissolved solids, but you'll notice the iron is at 2.5 ppm. We like to see iron less than 0.5 parts per million. And in order to avoid the things that can happen with water in terms of plugging nipple drinkers and those kinds of things. Well, just settling the water, doing absolutely nothing else, just letting it settle and then sampling it. In this case, it was 7 days later. We didn't need to go that long. Dropped the iron level from 2.5 down to 0.6. But 48 hours is sufficient time, especially if you do have an upstream chlorination unit in place. Disinfection is an area that I don't claim to be the most knowledgeable about by any stretch of the imagination. I'm going to show you a little bit of data later on some work we did with chlorination. Chlorination can be done with a number of compounds. Basically, we want to get the formation of byproducts of the chlorine, which are very effective disinfectants against many pathogens, but not all. In large industrial systems, they'll use chlorine gas, but those aren't typically used on a farm basis or on a house basis, because chlorine gas is just too dangerous to work with. And so typically then people will use sodium hypochlorite or calcium hypochlorite, depending on whether they want a liquid or a solid in the delivery system that they're using. There's also chloride dioxide, which is becoming a bit more common as well. Increasingly, one of the byproducts of chlorination is compounds called trihalomethane, TMH, and they are known carcinogens. So for human consumption, this process has to be managed very well. The TMHs are not an issue if there's no organic material present. But what happens is the chlorine binds with the organic material and gets converted over. And so that's a real concern in human treatment programs. So what they do is they will, upstream of chlorination, they will have filtration systems and so on to remove the organic material to prevent those compounds from being formed. But some people are still skittish about that. Every once in a while, they get into the press and can sometimes be over-sensationalized. So some municipalities are going to ozone treatment or to the use of ultraviolet rays as a way of disinfecting water. And those we're seeing them filter down onto pig farms and other sort of non-municipal uses. As we learn more about the technology, people become more familiar with it, and it becomes a little more available on that size and scale. So let's talk now about the effect that sulfates have on the performance of pigs. And as explained in my manuscript, when I was working in the feed industry, my first job after grad school, we encountered a lot of complaints about water quality in our business area, a lot of complaints. So when I left the feed industry and got into research, it was one of the areas that I really wanted to pursue and understand. And I learned a lot of lessons in that process. And one of the lessons that I learned is that what we believe to be true when we ask the pig isn't necessarily true. And there's great merit in asking the pig to answer the question than us trying to answer the question on the basis of what we observe. This is one of our earlier experiments, water that came from the city of Saskatoon, so it's river water, well treated. Then 2 water sources that were brought in from farms that were having problems with water quality, and we trucked them into campus, put them into storage containers, and then fed them to pigs. So you can see the total dissolved solids level very high, the sulfate levels very, very high. This would be considered sort of getting into closer to that danger area. The pH was kind of typical for that area. This really depends on the rock formations that water goes through when the aquifer is charged. You can see that in terms of average daily gain, pigs did not care. They grew virtually identically. There was no effect on feed to gain. Average water intake, going back to your question, and this totally surprised me. I mean, this surprised me. This really surprised me because they actually drank more of the high sulfate water than of the quote-unquote fresh water. And I guess when we thought about it, it makes sense because they are trying to excrete more minerals, right, through the urine, and so they're going to try to put more water through the system to do that. Now, going back to your question, what happens is that as we looked into it more and looked into data in other species and so on, that as the, we'll call it the salt content of water rises, initially intake goes up. And then it reaches a maximum, and then further increases in salt, water intake goes down, and goes down below the level of where they would drink fresh water. But if we've read books and, the old explorers, Vasco da Gama and people like that, they knew that they weren't supposed to drink seawater, but when they ran out of water, they drank seawater, and of course they died. Our physiological mechanisms tell us one thing, and our knowledge of science is something else. Okay, so that's something to keep in mind, and we did see that in many subsequent experiments. Quite surprising. However, notice the performance was equivalent, and these were 4-week-old pigs, by the way. But look at the scour scores, scored from 1 to 3. These pigs, there was a number of pigs that had, we'll call it profuse diarrhea, very watery diarrhea. So we saw diarrhea, but we did not see changes in pig performance. And that's a common theme. That we did that study, we did subsequent studies on campus. We went out to a farm, smaller scale study, and we continued to see the same results. We didn't believe it. The producers we were talking to didn't believe it. And finally the opportunity came up to do a study on a commercial farm, and it was just, figure, there is a God, and he was looking out for me because he gave me an opportunity to work on a 1200 sow fair to finish operation, which already had an RO unit in place. So we had the untreated well water, and then we had the RO treated water on this farm. And so you can see total dissolved solids in the well water was coming out at over 3,000 parts per million, and the RO treated water, we brought it down to 219. Pretty darn good quality water. Sulfates were reduced from 1650 down to 29. pH is brought down. Again, by removing some of the ions, we can expect that to happen. Hardness was reduced dramatically. Bicarbonate obviously went down. There were no real nitrates to worry about. This is just noise, okay, not something we'd get worried about. But all of the ions were reduced, and even the iron was reduced from 7 to 0.4. That was the level of iron that was in the water that was destroying the filters in the RO unit that had to be handled. Okay. So here's the results of experiment number 1. The way this farm operated, they were weaning at 3 weeks of age. The sows were removed from the crates, and the pigs remained in the farrowing crates for 5 weeks after that. So we started the experiment the day of weaning and continued on, I think it was for 4 weeks after that. What else can I say? The water delivery system was by pair of crate. So we had, was it 12 and 12, I think it was. So we had anyhow good replication because it was weekly farrowings on a 1200 sow unit. Because we had the opportunity, people were asking questions those days about dish drinkers, so we had our standard nipple type drinker and then a dish type drinker in half of the crates. So the pig started around 13 pounds, the final weight around 47 pounds. Average daily gain, there was no effect due to water, and there was no effect due to drinker. There was, in terms of feed efficiency, there was an effect of the drinker, but there was no effect of the water. You can see 651, 650, 672, 673. Now, in my previous slide, I showed water intake because we could adjust for waste. On this farm, we couldn't, so we call it water disappearance. And in any data that you're looking at on water consumption, so to speak, please make sure that they tell you whether they've measured water intake, meaning they have corrected for waste, or they're just really measuring disappearance. Because as you can see here, there was a tremendous drop in water disappearance with the dish drinkers, which is really no surprise, and lots of people have seen that since. But in our view, all we probably did was reduce wastage by that much. Okay, so I don't think but we really have no way of saying whether we affected water intake because we didn't adjust for waste. I know one paper that I read where they talked about it referred to water intake, and we asked the author, we contacted them about whether this was intake or disappearance, and he said no, it was actual intake. So we emailed him back and said, well, how did you adjust for waste or measure waste? And he said, well, we really didn't measure it. We just assumed that 20% of the disappearance was waste, so we took 20% off of the disappearance and called it intake. So have to be careful what's published. The producer didn't believe those results. And so he said we have to rerun the trial because this isn't possible, because he and everybody working in the barn knew dang well that these pigs were performing poor on the non-RO water. Mind you, if I was pork producer and I'd invest $100,000 in an RO unit, you obviously believe that it was a serious problem. And so we reran the study. In this case, we decided to do it with and without zinc oxide in the feed because they thought that might have been a variable. But again, there was no effect on average daily gain. There was an interaction between water and zinc, and you see that right here with the untreated water. The added zinc actually lowered average daily gain, but with the RO treated water didn't have any effect. And I'm not sure. Whenever you run an experiment, we sort of have to be careful that if you measure enough things, just by serendipity, something's going to be different. That's just random error, what we call beta error. And so we have to be careful that it kind of fits in with all of the other data that we see. And we did wonder about that. In terms of gain to feed, there was no effect. So again, 2 large-scale studies and absolutely no benefit to removing the sulfates and the other minerals from the water.
Did they do oxidation prior to filtration?
No, because they were doing RO. So but they did have a cistern in place, but they were doing chlorination, and it was in the cistern, and then they did the reverse osmosis after that. Okay.
For how long do the pigs best last month production?
I'd say no. It would have been 4 weeks, I believe. 28 days starting with weaning at 3 weeks of age. I think that about looks right on the data too. I could look that up for you. Okay.
That was in the initial slide from the stuff that you did on the university. That you'd taken a clinical score, so like clinically there was a scour score, a lucid difference in the stools. Was that, you remember, was that clinically apparent?
Yeah, well, I don't have that data, Roger, and we did dry matters, actually, to be a little more objective. And, I mean, these pigs here had huge diarrhea. And you walked into the nursery.
In both groups? Or?
Yes, in both experiments. Oh, yes. In both cases, profuse diarrhea. And indeed, when you walked into the nursery and looked at the pigs, you knew without looking at the water line which pigs were on which treatment. They were filthy. And they looked terrible. And that's the problem, Roger, right? And that's where we learned the lesson, the ultimate lesson, was the pigs can look terrible, but they can perform equally. And we have to be very, very careful about that. And so then the real take-home message to me is we have to be really careful what we do to manage water quality, that we are not doing things to manage water quality which actually impairs pig performance more than the water is. And we would see examples of that where people would do things, put oats in the starter diet, right? Well, it helped to reduce diarrhea, but it also slowed growth rate down tremendously. So it's a challenge. And I know as veterinarians, people in the feed industry, anybody consulting with producers, this is an extremely hard message to deliver. And I mean, the producer here, well, certainly the people in the barn still don't believe the results after doing the trial twice, you know. And so it's just we're so ingrained that if pigs are scouring, they're not performing very well. We looked at some other things as well. We did a lot. This was published in Journal of Swine Health and Production in 2004. We took a number of pigs and we analyzed the carcass, the brain, the kidney, muscle, liver. We did extensive measurements in the blood. We saw in a few of the tissues there was an increase in the calcium in the tissue, which we couldn't understand. It was in more than one tissue. It was 2 or 3 tissues, but we didn't see any effect on any of the other mineral levels in the tissue. One of the things, I don't have the data on slide, but we also measured digestibility. So we put marker into the feed. We collected feces. When I say we collected the feces, I'm using the royal we because it wasn't me. But Spence, you know how that works in my lab. Right? Anyhow, we collected fecal samples and analyzed it, and we measured digestibility of dry matter and digestibility of energy, and they were absolutely identical on both groups. There was no change in digestibility. So that was consistent with seeing no change in feed efficiency. In the muscle, we didn't see change in any mineral levels at all. My last trial was done by Dr. Martin Nyachodi at the University of Manitoba, and this is a little bit different, but I thought I would share it with you. It was published in the Canadian Journal of Animal Science, so didn't get a lot of people may not have seen it. This was 3 trials run again in a commercial nursery, large-scale nursery, and compared in the first 2 experiments surface water, i.e. water from a dugout, snow runoff, rain runoff, and so on, versus well water, which was really water that was trucked in from a local municipality and had been treated, versus this same surface water over here that had been acidified by adding a commercial acidifier to the product. And the real interest was there any improvement? Would this producer improve his performance of his pigs if he hauled water from the local municipality rather than use the surface water? And as you can see, in terms of growth rate and in terms of feed efficiency, there's maybe a little bit here, but that was not statistically significant. But if anything, the surface water was better than the well water. And again, in the second experiment, there was no real advantage either. So in the third trial, what might be of interest, we had the acidified surface water versus the surface water. But we also looked at a system that was removing turbidity and chlorinating, and there was an error made in chlorination, and instead of getting free chloride in the range of 0.3 to 0.5 ppm, which is what you'd like for disinfection, we actually ended up with 2 ppm of free chlorine, so considerably higher than is recommended, and there was no effect on the pigs at all in terms of growth rate or feed efficiency, which surprised us, but it was nice information to have nonetheless. It was the kind of error that happened on this farm is the kind of error in chlorination that can happen in any circumstance. So the take-home messages then, first off is that water fills diverse and essential roles in life, and it's able to do that because of its very unique chemical structure. Secondly, that water quality standards are more often related to aesthetics than they are to health issues. And as practitioners, when you're going out to a farm and you're looking at water assays, that needs to be taken into account. And then thirdly, water high in sulfates may or indeed will lead to osmotic diarrhea, but this diarrhea, we never saw it associated with any impairment in performance. There were studies that have been done prior to our work and have been done since our work, and they found exactly the same thing. I'd like to just put in, if I may, just a quick plug. I hope you're all aware, but if you're not yet aware of the International Conference on Feed Efficiency in Swine, it's a joint effort of Kansas State University and Iowa State. It'll be held in the Quest Center in Omaha, Nebraska, in the Hilton Hotel on November 8th and 9th. The objective there is to take what we think is a timely subject of feed efficiency in swine and look at it from every perspective possible. So there's various aspects of nutrition like amino acid nutrition, energy nutrition. There's feed processing, looking at the effect of health and disease management, immunology, physiology, genetics and genetic selection, in-barn management and overall barn management, and health status and their effects. I think there's 14 presentations in total just on feed efficiency. We think it would be of interest to not only producers, but to veterinarians, nutrition consultants as well, other academics. Certainly we hope to get a lot of graduate students there to attend. And if you want more information, here is our website. And I can tell you from experience, ICFES has to be capitalized. It doesn't work if it's not. And but please feel free to contact me or Mike or Joel if you have any questions on that as well. Thank you very much. I appreciate the opportunity to talk about one of my favorite subjects, and if you have any questions, I'd try to answer those as well.